All right, 5.6 is called Hess's Law, and what this gets into is how to calculate heat without a calorimeter. You often don't want to have to go through and do the experiment every single time to try and get a heat value for a certain reaction. It will be a lot easier if we can actually use other reactions to find these heat values that I need. So what we do for Hess's Law here is we're going to calculate without a calorimeter. You use known heats for different reactions. So it shouldn't matter. For a set reaction, we have the same enthalpy value or delta H value every single time. Now it does matter as what your coefficients are, but if that equation is balanced correctly, it'll have the same delta H every single time. So all I have to do is look at what that reaction is, look it up, somebody else did the experiment for me, and then I'm good to go. Okay. Also, since enthalpy is a state function, that means I don't care how I get to my delta H value, I just need to get there. Okay, so it is not dependent on the number of steps that I take to get to that certain reaction. So what we do is we take 3 or 4 different steps to kind of make a net or overall reaction. And we're going to have some things, substances that are going to cancel out and they're going to be formed and then used up. And so you'll kind of see here we're going to have a bunch of different steps. So I'm going to use many different steps to get my delta H value. And any number of reactions with a known delta H value, okay, can be used to determine the delta H that I need. And you'll often see these delta H's written, since they're for a set reaction, as delta H with a little RXN on. So let's take a look at an example of this Hess's Law, and hopefully it'll make a little more sense. Okay, so for example, I have these 2 reactions, and then this is my net reaction. So the bottom reaction here is the reaction that I'm studying, and I took these 2 reactions, these 2 steps, and they made that bottom one. So what happened then is I added my 2 enthalpy values together, and that's what I get as the overall for this net reaction. And kind of in that diagram there, you'll see how that works. And so we've got this step plus another step will give my overall final product. And see how these 2 equal out the overall. And since water appears on both sides, it's canceled. So notice how I've got a water here as a product, and then I use it as a reactant. And notice how there are 2 waters, and they're both waters as a gas. So it gets made, and then in the next step, I use it all up. So in essence, it's canceled out, and I don't really care about what my water does in there. So you end up with your overall net reaction of CH4 plus O2 yielding H2O and CO2. And that's what we get right down here. Okay, so taking 2 steps and adding up to the third. So then that bottom number here, that negative 890, that is usually the number there that I am solving for that I don't know. I take these 2 steps that I know the delta H values for, and I solve for and figure out this bottom delta H value. And that is what we call Hess's Law. If I have a reaction that's carried out in a series of steps, the delta H for the reaction is the sum of the delta H for the steps. Now again, be careful with the delta H. It's sensitive to the states of matter you're in. Okay? And this allows us to calculate the enthalpy data for any number of reactions which are difficult to carry out. All you have to do is look at it and say, okay, I have these 3 reactions that'll make up that one, so I don't have to actually carry out that particular reaction that's actually a little more difficult to actually do. You do have to be careful with the delta H, okay, because there are a couple characteristics that you've got to watch out for. And the first one is that if you reverse the reaction, that means I have to reverse the delta H, and we'll see that here in an example. If you have to flip the reaction, that means you also have to flip the sign of that particular delta H that is associated with it. Because if you remember back to those energy diagrams or enthalpy diagrams, you're looking at now the reaction from the flipped point of view. Okay? The The second characteristic is that if you double or quadruple or half or third a reaction, that means you have to do that same to the delta H, because delta H is dependent on the amount with your moles. Okay, so if you have to double something, you got to double the delta H. So let's look at an example, and hopefully this will make a little more sense. Okay, the enthalpy of a combustion of C to CO2 is this negative 393.5. And the enthalpy for the combustion of CO to CO2 is negative 283 kilojoules per mole. Basically what is written right there. Using this data, calculate the enthalpy of combustion from C to CO. So we want to get these two steps they're telling us should add up to this third one. So you got to look at it and say, okay, what do I have to do to these to get them to add up? Well, what I usually look at with these is kind of the weird ones and make sure that they are on the right side. Meaning, I need carbon in my net reaction to be on the left. So this reaction here has to stay going this direction. I'm not going to flip this. I'm not going to flip the sign. But I need CO as a gas on the right side as a product. So what do? I look up here and I say, okay, well now CO is actually on the reactant side and the one that they give me. So what do I got to do? I need to flip this one. So if you take C plus O2, which is going to be the CO2, then I'm going to flip the bottom one. So now carbon dioxide is the reactant, and CO and 1/2 O2 are the products. Okay. Now when we look at these and try and add them together, look at what cancels. Okay. I see here I've got a CO2 on the right, I've got a CO2 on the left, so those are going to cancel. And notice how there's no CO2 in my overall that I want, so that's good. Now I've got half an O2 here and one O there, so that means that cancels and I'm with a half. And my overall then is C plus 1/2 O2 is going to yield CO. And that's exactly what I wanted to look for that particular reaction. So what do I have to do to these two to get that? Well, all I did was I flipped this one. So all I do is I flip, make that one the opposite sign, and then add them together. So negative 393.5 plus 283, because I flipped that bottom one, which gives me an overall of negative 110.5 kilojoules. Go ahead and try the next one. And you should get 1.9 kilojoules. All you had to do was flip the equation that had the diamond in it, and then you add the two together. Looking at the next reaction, this one has a little more involvement to it. Now I've got 3. Okay, so now I want to know the delta H for this particular reaction. That's my goal. So I look for something kind of weird, all right, which means I look at the carbon. So I know that this reaction here has got to stay going the direction that it is. So I'm going to start writing off that one. Then I look and say, okay, I know the C2H2 needs to be on the right side, which means I've got to flip this one here to get the C2H2 on the right, because none of the other ones have C2H2. So that's when we go and look at the third one and figure out, okay, what do I have to do to get there? Because I only need one H2 as a reactant, and I've got all kinds of other stuff. So right now, I've got 1 carbon dioxide on the right and 2 on the left. So I need to get these carbon dioxides to cancel out, which means I've got to take this one times 2, plus I also have 2 carbons. So if I take this times 2, that means I'm going to take this carbon one times 2. So now I've got the 2 carbon dioxides canceling, and I've got 2 carbons, which is good. I've still got 1 C2H2, so I want to leave that one alone, which means I need to get these waters to cancel, because I don't want water in my final one. So this one, the bottom one I haven't looked at yet, has water in it. So if I want the waters to cancel, I need water on the right side, which means I'm going to leave it alone. And let's see if that'll work out. So 5/2 O2, okay, is actually 2.5. So let's see if we get everything to cancel. My CO2s do, which is good. My waters do, which is good. And I've got 2.5 O2. That's going to cancel with my 5/2 O2. So I'm good. So I look now at everything I did and figure out. So this flipped, so I got to make this a negative. And this gets to be times 2. And then I add it all up, which will be a positive 1299.6 plus 2 times negative 393.5 plus negative 285.8, which should give me an overall of 226.8 kilojoules for that particular reaction. Go ahead and try the last one. You should get a negative 304.1 kilojoules because you're going to have to flip the second equation to get your O2s and O3s to kind of work themselves out. And then you're going to have to flip and divide the bottom one by 2 to get your O's and your O's2s to work themselves out. And again, you get the negative 304.1 kilojoules.